The industrial life cycle of aluminum foil begins with the strategic exploitation of terrestrial mineral deposits, specifically the sedimentary rock known as bauxite. This initial phase represents the fundamental transition from geological ore to a stabilized chemical intermediate known as alumina. Bauxite is primarily composed of aluminum oxide minerals such as gibbsite and boehmite, intermixed with iron oxides, silica, and titania. The extraction process is characterized by large-scale open-pit mining operations, an environment defined by the rhythmic movement of massive hydraulic shovels, the low-frequency drone of heavy-duty haul trucks, and the systematic removal of overburden. The objective of this stage is to procure a raw mineral substrate that can be chemically disassembled to release the metallic aluminum trapped within its crystalline structure. The refinement of bauxite into alumina is achieved through a multi-stage thermodynamic and chemical process known as the Bayer process. This operation is conducted within a massive interconnected network of pressurized steel vessels, heat exchangers, and precipitation tanks. The environment is one of clinical chemical discipline, defined by the persistent hiss of high-pressure steam, the slow rotation of massive agitators, and a pervasive alkaline atmosphere. The logic of the Bayer process is based on the differential solubility of aluminum minerals in a concentrated caustic solution, the kinetics of digestion, and the removal of impurities. The process begins with the mechanical reduction of the bauxite ore into a fine slurry. This slurry is then introduced into a high-pressure digestion vessel containing a concentrated solution of sodium hydroxide, caustic soda. Under temperatures reaching approximately 250 degrees Celsius and pressures exceeding 35 atmospheres, the aluminum minerals dissolve into the solution to form sodium aluminate. The non-aluminum components, primarily iron and silicon oxides, remain in a solid state, forming a waste byproduct known as red mud. The logic of this separation is absolute. The solid impurities are filtered out through a series of high-capacity sedimentation tanks and pressure filters. The remaining clear solution, rich in dissolved aluminum, is then cooled and directed toward the precipitation stage. The sound within the digestion department is a continuous high-pressure roar, a manifestation of the massive thermal and chemical energy required to break the molecular bonds of the Earth. Precipitation, calcination, and the synthesis of alumina. In the precipitation tanks, the sodium aluminate is seeded with fine crystals of aluminum hydroxide. As the solution is slowly agitated and cooled over several dozen hours, the dissolved aluminum begins to crystallize out of the liquid, forming large white clusters of aluminum trihydrate. This process is a study in slow-motion chemical organization, where the molecular structure of the mineral is reconstituted into a pure, standardized form. The final sequence of the refinement phase involves the calcination of the aluminum trihydrate. The crystals are fed into a massive rotary kiln or a fluid bed calciner and subjected to intense heat exceeding 1,000 degrees Celsius. This intense heat drives off the chemically bound water, leaving behind a fine, white, and exceptionally abrasive powder, aluminum oxide, Al2O3, commonly referred to as alumina. The state of the minerals at the conclusion of this stage is one of chemical purity. The bauxite ore has been stripped of its geological identity and transformed into a standardized industrial precursor, ready for the energy-intensive electrolytic reduction process. The Hall-Héroult process, electrolytic reduction, and the birth of liquid aluminum. The transition from alumina powder to metallic aluminum is achieved through the Hall-Héroult process, a continuous electrolytic reduction conducted within massive carbon-lined steel vessels known as pots. This phase is the most energy-intensive stage of production, requiring a constant and massive influx of direct current electricity. The environment of the pot line is one of monumental electromagnetic force and radiant heat, defined by the low-frequency hum of high-voltage rectifiers and the intense white-orange glow of the molten electrolyte. The logic of the reduction process involves the dissolution of the alumina powder into a molten bath of cryolite, sodium aluminum fluoride. This bath serves as the electrolyte, allowing the electrical current to pass through the solution. A series of massive carbon anodes are suspended in the bath, while the carbon lining of the pot serves as the cathode. As the current, often exceeding 400,000 amperes, passes through the solution, the oxygen atoms from the alumina migrate toward the carbon anodes, where they react to form carbon dioxide gas. Simultaneously, the metallic aluminum ions migrate toward the cathode, where they gain electrons and transform into liquid metal. The liquid aluminum, being denser than the electrolyte, settles at the bottom of the pot. At regular intervals, a specialized vacuum crucible is utilized to siphon the molten metal from the pots. The sound within the pot line is a monolithic atmospheric drone, a manifestation of the massive electrical energy being converted into chemical work. The temperature within the pots is maintained with absolute precision at approximately 960 degrees Celsius, ensuring the stability of the electrolytic reaction. Direct chill casting and the formation of primary ingots. The final sequence of the primary production chapter involves the stabilization of the liquid metal into massive rectangular blocks known as ingots. The molten aluminum is transported to a casting furnace where it is treated with specialized fluxing agents and degassing gases to remove any residual impurities or dissolved hydrogen. This chemical polishing is essential, as even a microscopic inclusion would cause a structural failure during the subsequent rolling of the foil. The metal is then cast using the direct chill or DC casting method. The liquid aluminum is poured into a shallow water-cooled copper mold with a movable bottom. As the metal begins to solidify, the bottom of the mold is slowly lowered into a pit and a continuous stream of water cooling is projected directly onto the surface of the emerging ingot. This rapid thermal reduction ensures a fine, uniform crystalline structure. A single primary ingot can weigh more than 25 tons and possess a length exceeding 9 meters. The state of the metal at the conclusion of this first chapter is one of structural readiness. The geological aluminum minerals have been extracted, refined, reduced, and stabilized into a massive metallic monolith. The ingot is no longer a mineral. It is a high-purity industrial substrate possessing the ductility and thermal conductivity required for the intense mechanical deformation that follow. The steady hum of the potline rectifiers and the rhythmic hiss of the casting water remain the constant acoustic backdrop to this industrial evolution, a testament to the scale of the energy required to synthesize aluminum from the crust of the earth. The movement of the primary ingots from the casting department to the scalping and preheating stations is the next logical step in the manufacturing cycle, marking the end of the chemical synthesis phase and the beginning of the mechanical rolling history. The transition of the massive primary aluminum ingots from the casting department to the rolling facility represents the first major mechanical intervention in the fabrication of aluminum foil. In this stage, the solidified metallic monolith, weighing more than 25 tons, is subjected to intense thermal conditioning and extreme compressive forces to reduce its thickness from several hundred millimeters to a mere fraction of its original dimension. This phase is governed by the principles of metallurgy and fluid dynamics, specifically the recrystallization of the aluminum grains under high-temperature deformation. The environment of the hot rolling mill is one of monumental scale, defined by the rhythmic roar of massive electric motors, the persistent hiss of high-pressure coolant sprays, and the intense infrared radiance emitted by the incandescent metal. The objective is to transform the brittle, cast structure of the ingot into a highly ductile, uniform strip known as a mother coil. The process begins with the scalping of the ingot. During the direct chill casting process, the exterior surface of the metal often accumulates oxides and atmospheric impurities that could compromise the surface quality of the final foil. To ensure absolute purity, the ingot is mounted on a high-capacity milling machine equipped with rotating cutting heads. These heads systematically remove a layer of approximately 10 to 20 millimeters from both of the large faces of the ingot. The resulting aluminum chips are collected and pneumatically transported back to the melting furnace for recycling. The sound within the scalping department is a high-pitched metallic whine, the acoustic manifestation of tungsten carbide teeth shearing through the solid aluminum substrate. The logic of thermal homogenization and the soaking pits. Before the mechanical reduction can commence, the scalped ingot must be brought to a uniform internal temperature to ensure consistent plastic flow. This is achieved within a series of subterranean furnaces known as soaking pits. The ingots are suspended vertically or stacked horizontally within these pits and subjected to a precisely controlled heating cycle. The temperature is gradually elevated to approximately 550 degrees Celsius and maintained for a period of several dozen hours. The logic of this soaking period is twofold. Thermal equilibrium, it ensures that the core of the massive ingot is at the same temperature as the surface, preventing internal cracking during the first rolling pass. Metallurgical homogenization, the prolonged heat allows for the internal redistribution of alloying elements, such as iron and silicon, ensuring a uniform crystalline structure. The environment of the soaking pits is one of profound, silent heat. The only movement is the slow circulation of high-temperature air driven by massive internal fans. Once the metallurgical stabilization is complete, a high-capacity overhead crane extracts the glowing ingot and places it onto the conveyor table of the hot breakdown mill. The mechanics of the breakdown mill and the reversing rolling sequence. The hot breakdown mill is a monumental engineering assembly consisting of a 2-high or 4-high rolling stand. In a 4-high configuration, 2 relatively small work rolls make direct contact with the aluminum, while 2 massive backup rolls provide the structural rigidity required to prevent the work rolls from bending under the immense pressure. These rolls are driven by twin electric motors that can generate several thousand horsepower. The rolling process is a study in incremental reduction. The ingot is passed back and forth through the rolls in a reversing sequence. During each pass, the gap between the work rolls is reduced, forcing the metal to elongate and thin. Initial passes. The first few passes are dedicated to breaking down the large as-cast grains of the ingot. The thickness is reduced from approximately 600 millimeters to 200 millimeters in a series of calculated steps. Intermediate reduction. As the ingot becomes longer and thinner, the rolling velocity is increased. The metal, now a glowing slab over 30 meters in length, begins to move through the mill at a rate of several hundred meters per minute. The sound of the breakdown mill is a deep, earth-shaking roar, accompanied by the percussive clap of the metal as it enters the rolls. To manage the immense friction and heat generated by the deformation, a high-volume spray of oil-water emulsion is projected directly onto the rolls and the metal surface. This emulsion acts as both a lubricant and a coolant, preventing the aluminum from sticking to the steel rolls and maintaining the thermal stability of the mill components. Metallurgical recrystallization and the formation of the strip. As the aluminum is compressed, its internal crystalline structure is radically altered. The grains are flattened and elongated in the direction of the rolling, a process known as strain hardening. However, because the metal is at a temperature exceeding its recrystallization threshold, new strain-free grains begin to form immediately after each pass. This dynamic recrystallization maintains the ductility of the metal, allowing it to be reduced to a final hot-rolled thickness of approximately 6 millimeters without fracturing. The logic of the hot rolling phase concludes with the tandem mill or the final pass of the reversing mill. The metal, now a continuous ribbon several hundred meters long, is directed towards a high-speed coiler. This device winds the incandescent strip onto a heavy-duty steel mandrel, creating a mother coil that can weigh more than 20 tons. The dynamics of edge trimming and precision coiling. Before the coiling is finalized, the irregular edges of the strip, which may have developed small cracks or a lagertering during the reduction, are removed by a pair of high-speed rotary shears. These shears act like industrial scissors, creating a clean, uniform edge that is essential for the stability of the subsequent cold rolling stages. The removed scrap is immediately directed towards a baling press for recycling. The sound of the coiling station is a rhythmic, high-frequency whirring, a mechanical counterpoint to the distant roar of the primary mill. The environment is thick with the scent of vaporized rolling oil and the shimmering haze of the cooling metal. The state of the metal at the conclusion of this second chapter is one of functional transition. The monolithic ingot has been transformed into a long, uniform, and ductile strip. It is no longer a block, it is a metallic ribbon, possessing the precise metallurgical profile required for the extreme cold reduction that follow. The mother coil is now moved to a cooling area where it will remain for several hours or days until its temperature reaches equilibrium with the ambient atmosphere. The steady hum of the cooling fans and the occasional metallic clink of the contracting metal remain the constant acoustic backdrop to this industrial evolution, a testament to the scale of the mechanical and thermal discipline required to reshape Earth's minerals. The movement of the mother coils from the hot mill to the cold rolling department is the next logical step in the manufacturing cycle, marking the end of the thermal deformation phase and the beginning of the precision cold reduction history. The transition of the hot-rolled mother coils from the cooling area to the cold rolling facility represents the most delicate and technologically demanding phase in the industrial fabrication of aluminum foil. In this stage, the metal strip, which possesses an initial thickness of approximately 6 millimeters, is systematically reduced to its final gauge, which can be as thin as 6 microns. This phase is governed by the principles of work hardening and hydrodynamic lubrication. Unlike hot rolling, cold rolling is conducted at temperatures well below the metal's recrystallization threshold, meaning that the crystalline structure is permanently elongated and compressed without the spontaneous formation of new grains. The environment of the cold mill is one of clinical precision, defined by the high-frequency whine of high-speed rollers, the clinical scent of refined mineral rolling oils, and the constant flicker of digital X-ray gauges. The objective is to achieve a surface finish of exceptional quality and a thickness tolerance measured in millionths of a meter. The cold rolling process is typically conducted across several individual mill stands or through multiple passes on a single high-speed universal mill. As the aluminum strip is forced between the work rolls, the intense pressure causes the metal to flow longitudinally, significantly increasing its length while decreasing its thickness. Because the metal is not heated, it undergoes a process known as work hardening or strain hardening. Each pass through the rolls increases the dislocation density within the aluminum's atomic lattice, making the metal progressively harder and more brittle. To maintain the ductility required for extreme reduction, the coils may be subjected to an intermediate annealing cycle, where they are heated in an inert nitrogen atmosphere to allow for controlled recrystallization. The role of rolling oils and hydrodynamic lubrication. A critical component of the rolling logic is the management of the interface between the steel rolls and the aluminum strip. At the high velocities utilized in modern mills, often exceeding 1,500 meters per minute, the friction generated by the reduction would lead to surface tearing and thermal instability. To mitigate this, a constant stream of highly refined rolling oil is sprayed into the roll gap. This oil serves two primary functions. Lubrication. It creates a microscopic hydrodynamic film that prevents direct metal-to-metal contact between the aluminum and the steel work rolls. The thickness of this film is managed with absolute precision, as it directly influences the final surface texture of the foil. Thermal management. It absorbs the heat generated by the mechanical deformation of the metal, transporting it to a centralized filtration and cooling system. The viscosity of the oil is monitored in real time, as even a minor deviation would affect the reduction efficiency. The sound within the cold mill is a persistent, high-pitched whistle produced by the high-speed movement of the oil-laden air. The environment is one of supreme industrial cleanliness, as even a microscopic particle of dust on the rolls would leave a permanent pinhole or blemish on the thin foil. The doubling process and the secret of the shiny and matte surfaces. As the aluminum strip reaches a thickness of approximately 30 to 40 microns, it becomes increasingly difficult to reduce further without the risk of the foil tearing under the tension of the mill. To overcome this mechanical limitation, the manufacturer employs a technique known as doubling. In this process, two separate webs of aluminum are fed into the final rolling pass simultaneously, one on top of the other. The logic of doubling is a study in industrial efficiency and surface physics. Mechanical stability. By rolling two layers together, the total thickness of the material in the roll gap is doubled, providing the structural integrity required to reach the final thin gauge specifications without breakage. Surface differentiation. This process is the direct cause of the characteristic appearance of household aluminum foil. The exterior surfaces of the sandwich, the sides that make direct contact with the steel work rolls, are subjected to extreme pressure and friction, resulting in a high gloss, mirror-like, shiny finish. The interior surfaces, the sides where the two aluminum layers make contact with each other, are not polished by the steel. Instead, they undergo a microscopic peening effect against the adjacent metal, resulting in a diffused matte finish. This differentiation is not a decorative choice, but a functional byproduct of the doubling logic. Following the final pass, the doubled web is moved to a separator or slitter, where the two layers are carefully unspooled and wound onto separate finished cores. The logic of automatic gauge control and X-ray metrology. To ensure that the foil maintains a perfectly uniform thickness across its entire width and length, the mill utilizes a closed-loop automatic gauge control system. This system relies on high-sensitivity X-ray or isotope sensors positioned at the entry and exit points of the mill stand. As the foil travels through the sensors at high speed, the system calculates the exact thickness based on the attenuation of the radiation beam. If the sensor detects a deviation of even 0.1 microns, it sends an instantaneous signal to the mill's control computer. The computer then adjusts several mechanical parameters. Roll gap pressure. The hydraulic actuators increase or decrease the force on the backup rolls. Strip tension. The coiler and uncoiler adjust their torque to stretch the foil slightly, which influences the reduction rate. Rolling speed. The velocity of the mill is modified to alter the thickness of the hydrodynamic oil in the roll gap. This level of metrological oversight is a fundamental requirement of the manufacturing logic, as a non-uniform gauge would lead to failures in the subsequent converting or packaging processes. The environment of the control room is one of quiet digital scrutiny, where the only movement is the constant shifting of the data graphs on the high-definition monitors. Final annealing and the achievement of dead soft temper. The final sequence of the rolling chapter involves the final annealing of the finished foil. Because the cold reduction process has left the metal in a highly work-hardened and oily state, it is unsuitable for consumer use. The finished rolls are placed into massive batch furnaces and subjected to a prolonged heating cycle in an oxygen-free environment. This final thermal treatment serves three essential purposes. Temper control. It removes the internal stresses within the metal, transforming the brittle hard foil into a dead soft or semi-hard temper that can be easily folded and shaped by the end user. Oil removal. The intense heat vaporizes any residual rolling oils on the surface of the foil, ensuring that the metal is chemically clean and safe for food contact. Surface stabilization. It promotes the formation of a stable microscopic layer of aluminum oxide on the surface, which provides the foil with its characteristic corrosion resistance. The sound of the annealing department is a low-frequency hum from the furnace fans and the occasional clank of the heavy cooling racks. The state of the metal at the conclusion of this third chapter is one of functional perfection. The massive 25-ton ingot of the first chapter has been transformed into a delicate, high-purity membrane of specified thickness and temper. The aluminum is no longer a block of mineral, it is a metallic fabric, possessing the reflectivity, impermeability, and ductility required for the preservation of heat and the protection of global resources. The movement of the finished foil rolls from the annealing furnaces to the slitting and packaging department is the next logical step in the manufacturing cycle, marking the end of the metallurgical history and the beginning of the logistical deployment. The steady whine of the cold mill and the silent heat of the annealing furnaces remain the constant acoustic backdrop to this industrial evolution, a testament to the scale of the mechanical and thermal discipline required to thin the Earth's metal. The progression of the annealed aluminum rolls from the thermal stabilization furnaces to the finishing and slitting department represents the final mechanical articulation in the manufacturing cycle. In this stage, the massive, wide rolls, often exceeding 2 meters in width, are transformed into the specific narrow dimensions required for industrial converters and retail consumers. This phase is governed by the principles of high-speed tension control and shear-cut mechanics. The environment of the slitting department is defined by the high-frequency hum of rotary knives, the rhythmic movement of automated core loaders, and the clinical cleanliness required to maintain a sterile metallic surface. The objective is to achieve a burr-free edge quality and a winding tension of absolute consistency, as any deviation would result in the material tearing during high-speed packaging applications. The slitting process begins with the mounting of the annealed roll onto the unwind stand of a high-speed slitter rewinder. The logic of the slitter is based on the precise separation of the metal web using circular shear knives. These knives consist of a pair of overlapping steel discs that rotate in opposition, creating a clean, scissor-like cut as the foil passes through them. The width of each slit is managed by the positioning of the knife blocks along a high-precision lateral rail, with tolerances measured in tenths of a millimeter. The dynamics of foil separation and surface protection. A unique technical requirement occurs when processing the doubled foil produced in the previous stage. Because the two layers of foil were rolled together, they must be meticulously separated before being wound onto individual cores. This is achieved through a specialized separation station integrated into the slitter. The two webs are drawn apart at a specific angle, guided by a series of air cushion rollers that prevent the delicate surfaces from scratching or developing static cling. As the layers separate, the differentiation of the surfaces becomes visible: the shiny side, which was in contact with the steel work rolls, and the matte side, which was in contact with the adjacent aluminum layer. The logic of the separation involves a constant monitoring of the peeling force. If the force is too high, it indicates that the rolling oils were not fully vaporized during annealing, which could lead to surface defects. The sound in this area is a gentle, persistent rustle, the acoustic signature of millions of square centimeters of metal being divided. Winding dynamics and the management of air entrainment. The rewinding of the slit foil onto cardboard or metallic cores is a study of advanced industrial kinematics. As the diameter of the finished roll increases, the rotational speed of the core must be adjusted to maintain a constant linear tension. If the tension is too high, the foil will stretch or break. If it is too low, the roll will become spongy, leading to telescoping or edge damage during transport. A critical variable in winding thin-gauge foil is the management of air entrainment. At high winding velocities, often exceeding 800 meters per minute, a thin layer of air can become trapped between the layers of the metal. This air acts as a lubricant, causing the layers to slide and creating soft rolls. To mitigate this, the slitter utilizes a lay-on or nip roller that applies a calculated pressure to the winding roll, squeezing out the excess air and ensuring a tight, stable package. The environment is one of clinical oversight, where automated sensors detect any microscopic fluctuations in the roll's density. Final metrological interrogation and pinhole detection. Before the foil can be certified for logistical deployment, it must undergo a final quality interrogation. The most significant concern for thin-gauge aluminum foil, especially when intended for sterile medical or food packaging, is the presence of pinholes. These are microscopic perforations in the metal, often caused by tiny dust particles during the rolling process. To detect these anomalies, the slitter is equipped with an online pinhole detector. This system projects a high-intensity light beam onto one side of the moving web, while a bank of ultra-sensitive optical sensors monitors the opposite side. If a single photon of light passes through the foil, the system records the exact coordinate of the perforation. The logic of the detector is absolute. If the number of pinholes per square meter exceeds the technical threshold, typically 0.5 for high barrier applications, the roll is diverted for recycling. Logistical packaging and the prevention of oxidative degradation. The state of the metal at the conclusion of this fourth chapter is one of total transformation. The journey began with the excavation of bauxite from the Earth's crust, followed by the chemical refinement into alumina, the electrolysis reduction into molten metal, and the monumental thermomechanical deformation of the hot and cold rolling mills. Each stage required a massive investment of thermal, electrical, and mechanical energy, governed by the absolute logic of metallurgical science. The aluminum is no longer a geological mineral, it is a metallic fabric of specified gauge and temper, possessing the unique ability to reflect thermal energy and block the passage of oxygen and light. It is a standardized technical tool for the preservation of human resources and the efficiency of global thermal management. The steady roar of the primary pots and the rhythmic whine of the slitter rewinder remain the constant acoustic memory of this industrial evolution, a testament to the scale of the discipline required to thin the Earth's metal to the thickness of a human hair. Every square meter of finished foil represents a triumph of industrial synthesis, moving from the silent heat of the smelting pots to the clinical precision of the finishing lines. The material is now ready for its service life, a temporary but essential participant in the protection and organization of the modern world. The conclusion of the industrial life cycle of aluminum foil does not represent the termination of the metallic substrate, but rather its transition into the secondary metallurgical cycle. This phase is governed by the principles of circular thermodynamics and the conservation of elemental energy. Aluminum is unique among structural metals for its ability to be recycled indefinitely without the degradation of its inherent physical properties. The environment of the secondary smelting facility is defined by the rhythmic operation of massive magnetic sorters, the low-frequency hum of induction furnaces, and the intense thermal radiance of molten recovery baths. The objective of this final stage is to reclaim the aluminum from post-consumer and industrial waste streams, requiring only a small fraction of the original energy expended during the primary electrolytic reduction. The logic of aluminum recovery is predicated on the vast energy differential between primary and secondary production. While the initial extraction from bauxite requires a massive electrical influx to break the chemical bonds between aluminum and oxygen, the secondary melting of existing metal requires only approximately 5% of that original energy. This energy efficiency is a fundamental requirement of global industrial sustainability, transforming discarded foil and scrap into a high-value metallic resource that can be reintegrated into the rolling mills of the previous chapters. The mechanics of systematic sorting and shredding. The recovery process begins with the mechanical organization of aluminum waste. Discarded foil, containers, and industrial trimmings are collected and transported to a centralized processing facility. The first stage involves the systematic removal of non-metallic contaminants, such as plastic laminates, organic residues, and ferrous metals. This is achieved through a multi-stage sorting manifold. Magnetic separation. Massive overhead magnets extract any steel or iron components from the moving waste stream. Eddy current separation. This is a study in electromagnetic physics. A rapidly rotating magnetic field induces eddy currents within the non-ferrous aluminum fragments, creating a repulsive force that physically ejects the aluminum from the waste stream while allowing non-conductive materials to fall away. Mechanical shredding. The reclaimed aluminum is then directed into a high-torque shredder, where a series of rotating steel blades reduce the disparate fragments into uniform chips or shreds. The sound within the sorting department is a chaotic percussive sequence of metallic collisions and the high-pitched whine of the eddy current rotors. This mechanical preparation ensures that the material fed into the furnace possesses a high surface area to volume ratio, which optimizes the melting efficiency. The thermodynamics of decoating and thermal preparation. Before the aluminum shreds can be melted, Any residual organic coatings, such as the inks, lacquers, and plastic films often found on packaging foil, must be removed. This is achieved through a process known as decoating or thermal delacquering. The shredded aluminum is passed through a rotating kiln and subjected to a precisely controlled stream of hot gases at temperatures reaching approximately 500 degrees Celsius. The logic of this thermal treatment is to vaporize the organic contaminants without oxidizing the aluminum metal. The resulting gases are captured and directed toward an afterburner where they are combusted to provide the thermal energy for the kiln itself. This self-sustaining energy cycle is a hallmark of modern secondary metallurgy. The sound of the decoating kiln is a steady, rhythmic roar, a manifestation of the high-velocity gas movement and the tumbling of the metallic chips. At the conclusion of this stage, the aluminum is chemically clean and ready for the final phase of thermal synthesis. The induction furnace and the synthesis of secondary ingots. The melting of the clean aluminum scrap is conducted within a massive induction furnace or a sidewell reverberatory furnace. Unlike the primary reduction pots, these furnaces utilize thermal energy to transition the solid metal back into a liquid state. The induction furnace employs a high-frequency electromagnetic field to induce internal heating within the aluminum, a process that ensures a high degree of thermal uniformity and minimizes the formation of dross or surface oxides. As the metal reaches its melting point of approximately 660 degrees Celsius, it forms a glowing silver-white pool. At this stage, specialized alloying elements may be added to adjust the chemical composition, ensuring that the secondary metal meets the exact specifications required for its next intended application. The liquid metal is then refined using a gas injection system that bubbles nitrogen or argon through the bath to remove any dissolved hydrogen, a process known as degassing. The liquid metal is then cast into secondary ingots or seaux using the same direct chill casting methods described in the first chapter. The sound of the smelting hall is a monolithic low-frequency hum from the induction coils and the occasional hiss of the degassing lines. The environment is one of profound radiant heat, marking the final stabilization of the reclaimed metal. The eternal recurrence of the metallic substrate. The state of the aluminum at the conclusion of this fifth chapter is one of total renewal. The atoms that were once a thin-gauge foil protecting a consumer resource have been reclaimed, purified, and reconstituted into a solid metallic monolith. The metal is now indistinguishable from primary aluminum, ready to be scalped, preheated, and rolled once again into a mother coil. The life cycle of the aluminum substrate is a study in eternal recurrence. The geological journey that began in a bauxite quarry has transitioned into a closed-loop industrial cycle. Every square meter of foil is a temporary manifestation of a metallic energy that is never truly consumed, only reshaped through the application of thermodynamic and mechanical discipline. The steady hum of the induction furnace and the rhythmic clatter of the sorting lines remain the constant acoustic memory of this industrial evolution, a testament to the scale of the precision required to preserve the Earth's resources. The movement of the secondary ingots back to the rolling facility is the final logical step in this narrative, marking the completion of the metallic history. The material is now poised for another billion rotations through the mills, a silent and essential participant in the ongoing organization of the modern world. Every reclaimed ingot represents a triumph of circular logic, ensuring that the energy and effort expended by human civilization are preserved within the unbreakable molecular structure of the metal.